Well, good afternoon, everyone. Thank you for joining us today. I have my notes. Today, we're going to be talking about revolutionizing concrete, the growing might of carbon allotropes in sustainable construction. Along with graphene, we're going to be discussing carbon nanotubes and carbon nanofibers. Again, my name is Shaun Lane. I'm the founder and CEO and president of NanoCrete. And before I get rolling, I want to thank ACI for the opportunity to talk at this conference with all of you and for the invitation to present, and more so for ACI's continued leadership in this industry. Over the next 20 minutes or so, I'll give a brief background about myself, a brief history about these allotropes, and the motivations behind implementing these technologies, the purpose and learning objectives from the relevant case studies I'll be sharing with you, and finally I'll wrap up with a brief summary with some questions as well. And again, my name is Shaun Lane, and really you could categorize me as a late bloomer concrete enthusiast. I come from the insurance industry, if you can believe it. I spent the last 8 years as an independent insurance broker. During the pandemic, I was reading about a lot of problems with concrete going forward, but more importantly, I have been a graphene enthusiast since about 2010. I first learned about graphene, and in the years since, I just keep reading about more and more some of the wonder properties that graphene could bring. So fast forward to 2022, I founded NanoCrete to develop innovative graphene-enhanced supplementary cementitious materials. So again, the purpose today is to discuss all of these recent techniques, material requirements, specification activity, procedures related to structural material aspects of CNTs, CNFs, and graphene. And spoiler alert, I'm going to abbreviate carbon nanotubes and carbon nanofibers, CNTs and CNFs. Just get that out of the way now. Describe the emerging technologies that are possible with this technology, and summarize the case studies related to the deployment of CNFs, CNTs, and graphene into concrete. Why should anyone care? Really, the problem is because of coal plants shutting down, previously low cost, easily sourced fly ash is becoming scarcer, adding to material costs. Now, if you compare that trend to other new SCMs like these carbon allotropes, they are becoming exponentially more available, helping to reduce costs. Now, some of these statistics, we've probably seen derivations of these statistics before, but really what it boils down to is our infrastructure sucks. The American Society of Civil Engineers actually rated our infrastructure a C- in 2021. Now, I don't know about you guys, but America, the country that launched probes to the furthest edges of our solar system, we should be able to produce concrete that lasts just as long as what the Romans did thousands of years ago. Other motivations, states like where I'm from, Colorado, Utah, Montana, Texas, and Florida, they face differing levels of convergence of these problems due to rapidly rising populations. And of course, states are doing what they can to stay on top of their maintenance costs, but of course states' dollars are stretched too thin, so they can only do so much. Utilizing carbon allotropes like graphene, CNTs, and CNFs in concrete can help reduce the carbon footprint of a project compared to regular mixes using standard SCMs. The enhanced strength and durability of carbon allotropes the enhanced strength and durability of carbon allotrope enhanced concrete enables overall resource and labor efficiency, helping to increase profits. And because these carbon allotropes can be produced from carbon-rich waste materials nearly anywhere, the need for mined or extracted materials for traditional SCMs and their respective supply chains is also greatly reduced. Moving on to today's first objective, to discuss these techniques and requirements. A little bit of history of these three materials. Graphene was discovered in 2004, and a fun fact, graphene was discovered when researchers applied Scotch tape to graphite. And you can actually do this yourself. Luckily, today, graphene is able to be produced at significantly larger quantities than Scotch tape and graphite pencils. Now, graphene has had a renaissance in production in the last few years because it was recently discovered that you can produce graphene from biochar, and biochar itself can be produced through a relatively well-known process called pyrolysis. So we're staring at the prospect here in the next 5 to 10 years of having the supply of graphene, high quality graphene, increase multiple orders of magnitude, which is what personally I'm excited about. Definitions. Okay, what is an allotrope, you might have asked? Allotropes are, simply put, differing microstructures for a particular element, in this case carbon. Now the three we're discussing today, as I've mentioned, graphene, carbon nanotubes, and carbon nanofibers, they're not the only carbon allotropes. You guys know about diamonds. Those are the shiny ones. Graphite, which is just like diamond, only much, much less dense. And another one of my favorites are buckyballs, or Buckminster fullerenes. Those are really cool. What we're going to do is break down what makes each of these different, their benefits to concrete, as well as look at what potential negative side effects could be. What is a microstructure? Well, I love this word. It is the structural inhomogeneities that may consist of spatially distributed phases of different structures, grains of different orientations, or structural defects. The carbon atoms in these allotropes are connected through covalent bonds. I'm not telling you anything you don't already know. Now, there's not a test later, but if you do find me afterwards, I will ask you to spell inhomogeneities. Here, as we can see, are the different structures. We have the three-dimensional for diamond as graphite, and a hybridized two-dimensional for the nanotube, carbon nanotubes. Why I like graphene is it is the only truly two-dimensional allotrope for carbon. And the reason why it is unique is because you're able to increase the surface area, functional surface area of contact by multiple orders of magnitude. Now, why do these structures matter? It's the magic happens at the microstructure, bottom line. And I want to stress this. The microstructures and the bonds between the carbon atoms in these allotropes is what provides the functional benefits and the functional performance enhancement in concrete. Graphene can't stop bullets. I don't know where that rendering come from. That's a neat rendering, but graphene does significantly increase the strength of materials when it is implemented. Some of the negative side effects, however, is stability and suspension. This is something that we're working on right now, is creating a successful inert delivery mechanism where the graphene is stable in suspension. Carbon nanotubes. What makes carbon nanotubes different than graphene is at the microstructure. All it is graphene rolled up into a three-dimensional cylindrical shape that can either be single or multi-walled. Multi-walled carbon nanotubes are more desirable than single-walled because of their robustness as well as their increased ability to withstand chemical attacks at the nanoscale. And it's been shown that carbon nanotubes have a Young's modulus order between 270 and 950 gigapascals and a tensile strength of between 11 and 63 gigapascals. Carbon nanofibers. These are different from the other two, and more so that structurally these are a lot more defective, if you will. They're not as clean as, they don't have the same clean carbon bonds as the other allotropes. The other main difference is that carbon nanofibers are themselves able to be delivered in a dry vehicle, dry mechanism for concrete itself. In case you hadn't noticed what some of the benefits are between all three of these, you have high thermal conductivity, high electrical conductivity, high elasticity and flexibility, high hardness, high chemical resistance, and antibacterial. I want to stress that is the similarities between all three carbon allotropes in this case. As you look at these fresh and hardened properties, once again, keep in mind it is because of the microstructures and the bonds between the carbon atoms in these allotropes that help achieve these properties. The case studies we're going to discuss, as well as the ongoing research into these materials, are helping to precisely quantify these improvements, which will be important for specifications. And here's some examples of where these carbon allotropes have been implemented already into concrete applications. As a company, we're looking at shotcrete first and foremost because of graphene's ability, purported ability, to significantly reduce rebound and dust. So that's what we're most excited about. Speaking of specification, it's been mentioned here before, for these innovative materials to be implemented at scale throughout this industry, there has to be a mutually agreed upon, like I say, testing specification. I'd like to say that ACI is leading this effort, as well as RILAM, the International Union of Laboratories Experts in Construction Materials, Systems, and Structures, as well as the 3DCP. It's actually an open source outlet for all research and relevant data related to the 3D concrete printing industry. And for graphene specifically, there's a lot of charlatans in this industry because it is fairly new in terms of advanced material. There's a lot of graphene manufacturers and suppliers. All they're doing is selling graphite. So the Graphene Council helps validate graphene manufacturers, suppliers, and companies like ours to ensure that transparency and legitimacy in this industry. So you can't just say you're using an advanced material when you're using a cheap alternative. What to ask? I mean, this is all great. All this technology is wonderful. The bottom line is that in terms of cost, if adding these materials are going to increase your project's cost by over 25%, it really doesn't matter what type of end properties the material has. The challenge is implementing these materials cost effectively while still having those increased performance results. But if you had to ask, or if I had to pick one, I'd say the last question is probably the most important, because if there's no buy-in from the guys on the job site, it doesn't matter if ownership or management loves this technology and really wants to use it. Everyone's got to be bought in. Moving on to our second learning objective today, I'm going to share with you some new research that's coming down the pike and that has already been conducted in this space. The Department of Defense, actually, is really keen on research for improving blast resistance of their structures, as well as improved cementitious materials for their forward deployed 3D concrete printers. Now, the evaluation study I found very interesting. They showed that adding 0.4% weight of cement of carbon nanotubes resulted in an increase of 40% compressive strength, 30% tensile strength, 15% flexural strength, and a denser microstructure. So something to keep in mind when looking at carbon allotropes is we're talking very, very minimal amounts of material implemented to achieve your desired results. And again, the point of showing you these very studies is to reinforce the point that there is an increasing number of papers being published in this space related to the effects of these carbon allotropes into concrete and as cementitious materials. On to our final learning objective today. We're going to discuss 3 relevant case studies for each of these carbon allotropes and then briefly summarize their results. So first, out of the University of Alaska, we have work done adding graphene oxide to pervious concrete. And here in this photo, you can see the second and the fourth cylinders are the ones with the graphene oxide implemented. So visually, there's no visual difference. So a complaint, or I guess a question I get when talking with contractors is implementing these carbon allotropes, is it going to darken our material? Is it going to darken the product? Is it going to ruin the color? But since we're talking such little implementation levels, 0.1%, 0.4%, the maximum I've ever seen is 1% weight by volume of a carbon allotrope being added. At those low dosage levels, you're not going to see any coloration changes. But the main takeaways from this particular case study is that the graphene oxide was chosen specifically for its 2-dimensional structure and its corresponding high aspect ratio, as well as its hydrophilic nature. As I just said, 0.1% additional weight by binder by adding this material. That 0.1% weight increase resulted in, after 28-day compressive strength, well, let me back up. The 28-day compressive strength was increased for the graphene oxide and cement enhanced material by 28%, and then 58% increase for the graphene oxide and the fly ash. For our second study, through the University of Colorado, Denver, we have implementing liquid CNTs for the city and county of Denver as a liquid admixture. Now, while cheaper water-reducing admixtures were available, the city and county of Denver was primarily interested in testing two different proportions of this liquid admixture for their project. They were interested in its potential not only as a means of increasing its resistance to the freeze-thaw cycles, but also to reduce overall maintenance required for this high traffic section of road. How well did it work? Well, the 2-gallon per yard mix saw the 7-day and 28-day strengths increase by 19.6% and 11.7% respectively. The 3-gallon per yard mix had its 7-day and 28-day compressive strengths increased by 9% and 26%. All that means is replacing equivalent amount of water with this liquid carbon nanotube admixture, you saw those strength increases after 7-day and 28-day. And how it looks, the top the top photos were for the 2-gallon per yard, and then for the bottom photos were for the 3-gallon per yard. So once again, from a visual standpoint, you wouldn't be able to tell that advanced materials were being implemented into this project. The key takeaway here is that the concrete enhanced with this liquid suspension CNTs can potentially save money in the long term due to reduced maintenance costs and a longer functional lifespan. All right, and for the third and final case study today, for the University of Houston, we go looking at their work at self-sensing carbon nanofiber concrete columns subjected to reverse cyclic loading. The carbon nanofibers in this particular instance were placed throughout the bottom and they were placed throughout the steel reinforcement cage at the column and at the base. Why these carbon nanofibers were chosen was to produce and provide a low-tech method of providing structural health monitoring while also increasing strength and ductility. Sorry. How did it work? Well, the CNFs, they were able to, because they show a relationship between electrical resistance and concrete strain, the CNFs in this study successfully helped the structural health monitoring devices provide real-time information, including detecting and assessing damage levels. Okay. This is all great. Why should anyone care? It boils down to this. By increasing the performance of local materials with carbon allotropes that then go to produce functionally superior concrete for local construction, everyone from shotcrete to precast to ready mix can save on time, money, and labor. And wrap it up in closing, I want to thank everyone for your time today. And I want to share with you that there is actually an enormous opportunity to profitably implement carbon allotropes like graphene, carbon nanotubes, and carbon nanofibers into your projects. And by doing so, you get to ensure that concrete gets to play an increasingly valuable role as a 21st century building material.